I'll get started. Welcome back again, everybody, to lecture 8 of my half of the Axion Cosmology course. We're really getting into deep constraints territory now, so I'm going to increasingly not go through detailed calculations, but give you kind of a feel for what's going on and like a tour of things going on in the literature. In the last 2 lectures of this week, so this week has been Constraints Week, last week was Theory Week. The last 2 lectures of this week, we covered the cosmic microwave background and large-scale structure, constraints on both the QCD axion and fuzzy dark matter. And those constraints largely involve, either the early universe, or in the case of fuzzy dark matter, non-relativistic approximations. But they were very much cosmology, large-scale structure. So now I'm going to come back with a bit of a mixed bag of things that haven't been covered elsewhere and things that won't be covered by Jens. But we're also coming back into the local universe, but we're still sticking with purely gravitational probes. All constraints from interactions will come in the last 2 lectures starting tomorrow. So, okay, what gravitational probes are we going to talk about? Here's the reading. So the first 2 gravitational probes we'll talk about are from Klemeninsky and Rubikov, Polyakov, Ovanataki and Dubovsky and Brito. And these are fuzzy constraints that work on fuzzy dark matter and the lightest end of the QCD axion. And they're relativistic. So we're coming back to the full Klein-Gordon relativistic treatment rather than Schrödinger-Poisson. And we're going to be doing like bits of general relativity too. And then in the third part of today's lecture, I'll talk about mini clusters and microlensing, and some of this will be covered again in Jens's final lecture tomorrow. But I want it here for completeness. And this is the game local universe, but it's definitely QCD axion, and it's definitely non-relativistic. Okay, so here we are. First part, pressure and pulsar timing. So we're looking now at the Compton scale effects of fuzzy dark matter. So when we did all of our treatment in Jens's lectures and in the CMB at late times after the axion oscillations begin, we normally integrate out the time scale of the axion mass. So all of the fluctuations that we've seen giving rise to relaxation for fuzzy dark matter and halos happen on de Broglie timescales set by the mass of the particle and its non-relativistic velocity. But if we reinsert the Compton oscillations, we can express the local axion field in the following way. So phi of xt is phi of r. So I'm assuming that I'm in the Milky Way galaxy and I've taken some angle average. So my field's just got a radial profile. And then I have some oscillation at the frequency set by the mass, the Compton frequency. And then some local phase factor. And I'm neglecting the slower time variation on the de Broglie timescale. So on the de Broglie timescale, there would be some time variation of this phi 0 of r, but I'm neglecting that here. So the energy density in this case is static. So the energy density rho is half phi dot squared plus half m squared phi squared. And if you just substitute this solution in, you find that it's static because sine squared plus cos squared is 1. So rho of r is just a half m squared phi squared, phi naught squared. Thus in Poisson's equations, you would also find that the gravitational potential is static. So grad squared phi is just this time-independent piece, rho, 4 pi g rho. However, this is only true on timescales large compared to the Compton timescale. So, and to see that, consider the pressure. So this is just the local expression for the pressure. The pressure is a half phi dot squared minus m squared phi squared. And then you use your cosine 2-angle formula, and you find that this the pressure actually still carries oscillations, but at the frequency cosine 2mt. So it oscillates on timescales a little bit faster than the Compton time. This is the thing that in the background solution, when we compute things like the relative density, we integrate out this timescale and say that fuzzy dot, the axion dot matter has no pressure. It has equation of state 0. Actually, its pressure oscillates on 2 times the constant time. So when we then substitute this into Einstein's equation, which I'll do on the next slide, you find that an oscillating pressure leads to oscillating contributions to the gravitational potential. So how does that happen? So here is the relevant Einstein equation. So this is, we did cosmological perturbation theory in lecture 5. So this is just the relevant equation in Newtonian gauge. Here I haven't done perturbations in the density or the pressure. So I'm allowing, so this applies in the nonlinear regime for the matter, but still working just the first order in the gravitational potentials. So special relativistic, but not general relativistic effects. So small curvature, but any timescale or velocity you like. But I'm considering myself to be inside the Milky Way. So you take my equations from cosmological perturbation theory and drop anything that includes Hubble or time derivatives of the scale factor. This is the equation that you get for the Newtonian potential and the curvature perturbation. I'm using the same notation here as I used in cosmological perturbation theory, which is a different, these symbols are swapped relative to each other in the references. But you just need to look at the definition of the metric potentials to get it all right. So from this, we can now solve for the time variation of the metric potential. So we make an Anzac solution that the potential has a leading order time independent piece, which is the solution to the Poisson equation, plus a sine and a cosine oscillating piece with phasors. If you substitute this solution in, then you find that the time-dependent pieces of the Newtonian potential and the curvature potential have to match, phi equals psi. And I'm going to be ignoring the time-dependent contribution of the curvature perturbation psi. In Klemeninsky and Rubikov, they discuss this in a little bit more detail and show that it can be neglected. So now, okay, we just put in the 0th order solutions, phi and psi cancel. We can then solve for the time-dependent piece of the Newtonian potential phi, and the coefficient of the cosine term has this form written here, and phi c is pi g rho over m squared. Okay, and this has the right dimensionality. Rho has mass dimension 4, and g is 1 over the Planck mass squared. So we've got the right dimensionless quantity for the Newtonian potential. Okay, how big is this term? So we can estimate how big this term is relative to the time-independent piece using the Poisson equation. So the Poisson equation tells us that the time-independent part of phi 0 is g rho over k squared, just taking the Fourier transform on the left-hand side. So that tells us that phi c is phi naught times k squared over m squared. K squared over m squared is the typical velocity. That's just because k is a spatial derivative. That's the momentum operator. So that gives you mv. K gives you mv. So you see that k squared over m squared is of order v squared, and thus this time oscillating contribution to the potential is suppressed by the velocity squared relative to the time independent part. So this is why you tend to drop time derivatives of potentials when we take the non-relativistic limit. But this is why none of these terms appear in the Schrödinger-Poisson equation, but when we're including the relativistic corrections, they do. An oscillating Newtonian potential induces time delays between signals coming from different places. So we're imagining that we have some signal being sent to us, some oscillating signal coming from some distant source. And as it comes to us, it comes through this oscillating pressure. And then you have some other source emitting from a different location, coming through a different realization of the field. So the time delay to the signal along the line of sight takes the following form. It's this integral of omega minus omega 0 over omega, where omega is due to the oscillating potential. So here it is. Here's the expression for the integrand. And the integrand is just the difference between in the Newtonian potential from the time of from t0 and t. So if you move through an oscillating potential and you come out and the potential was different than when you went in, you experience some time delay. So this is just the same as the integrated Sachs-Wolf effect in the CMB. So normally if a light ray comes into a potential, it goes in, it gets redshift, it gets blue shifted as it falls into the potential, and then red shifted as it comes out. So if a light ray just goes through a static potential, it comes out completely unperturbed. But if the potential when you went out is a little bit smaller or larger than the potential when you went in, you don't get the same amount of red shifting back on the way out as the amount of blue shifting you got on the way in. And so this can change the overall frequency of light and end up with some blue shifting or red shifting, which can delay, which leads to a delay in the arrival of the peaks in the wave. Is it the same? I don't know. I don't know. I could look that up.
But here it's not necessarily a delay. So here it's just a variance between different signals, right?
It's a delay. No, so this is imagining that you have so we're thinking with pulsars we get a beat coming from the pulsar, but if one signal comes through and it doesn't pick up any difference in phi, but the next one does, they'll be shifted relative to each other.
Shifted by both ways, right? Not necessarily delayed. I thought at the end we have a variance in the signal, but not necessarily delayed one.
Mm-hmm. So in the end, we will use the variance, but this is the time delay of a single signal.
I guess you get a delay if you deepen the potential. You get an anti-delay if you remove the gravitational potential.
Yeah.
Until you have Roman structures, we have delay.
Right. Yeah. So when you average over going through many different oscillations, you won't get on average a delay, but you will get a variance.
Yeah.
Yeah. But for just a passage through a time-dependent potential, you would get a delay. If I just sent my signal in, and then I just artificially moved my potential down, it would come out at a different frequency than it went in, so it would look like a delay.
A different frequency.
Right, so a different frequency looks like a delay. So I send some pulse at some fixed frequency, which means that you receive the signals at that frequency. You receive one packet, say, every second. But now, if they go through this potential that I change in time, and say that makes the frequency longer, you would now see the pulses arriving at, say, once every 2 seconds. So the time delay is caused by the change in frequency.
It is necessarily a delay.
No, well, it could be an increase as well.
Yeah, okay, that's the point.
Yeah, it could also be an increase if the potential got shallower over time.
Yeah. So it could go
Yeah, delta T could be positive or negative.
Yeah.
Or bigger or larger than T.
Both.
Yes.
Okay. Okay, sorry. That was just
Yeah, I've called them both a delay, but really it's just a change in the arrival time.
Yeah.
Right. Okay, so here's the expression for the integrand. And this time delay oscillates at the frequency the potential oscillates. So it has a frequency of 2 times the axion mass, and it has an amplitude given by the following expression, which you can just work out from these integrands and our solution for 5 from before. So here here is the magnitude of the time delay is equal to pi g rho over m cubed times sine md, where d is the distance to the source. This is how many oscillations did you see along the line of sight, and delta psi is the difference in the local phase from the point of emission to the point of arrival. And this is the thing that vanishes when you take the variance. Okay, and then as I said, the frequency at which this time delay oscillates is 2 pi times twice the Axion mass, 2 pi to account for, I used h bar equals 1, not h equals 1. So the frequency at which it oscillates is 10 to the minus 9 hertz, and then proportional to the Axion mass. So this is significant for thinking about what you can use to measure this kind of time delay. So this is a cartoon of what you expect to see. What you can use is called pulsar timing arrays. So you've got a set of pulsars, and you know the frequencies that pulsars go at. They're sending a signal to you as they rotate, and the beams, the jets cross the line of sight. But each pulsar in your array sees a different path. So each one sees a different time delay. So you can use this to try and measure these type of time delays. This isn't a new idea for fuzzy dark matter. What was, in fact, it's a common way. It has been proposed for a long time, hasn't been done yet, as a way to detect gravitational waves. So gravitational waves also involve fluctuations of the metric, but they're tensor fluctuations rather than scalar fluctuations. But the gravitational waves also induce time delays into pulsars. Gravitational waves induce a time delay with amplitude given by the following expression. Hc is the dimensionless strain of the gravitational wave. Omega is its frequency. So this is the thing that you replace with 2m for the axiom. Has a similar expression for the amplitude, and then the theta and psi in this expression are angles to do with your relative position, your relative orientation compared to the polarization and direction from which the gravitational wave is coming from. So this is a way that has been proposed to try and detect a stochastic background of low frequency gravitational waves. There hasn't been a detection of them, but there are results, and I'll show you them. So these pulsar timing arrays search for gravitational waves using this method. They have a good sensitivity at very low frequencies, and I'll show a plot shortly. And so if we take the RMS of this signal and of the Axion signal, we can basically just read off the expected constraints on fuzzy dark matter from if we're given a gravitational wave forecast for a particular frequency omega and a particular strain hc. We can just say, okay, omega is 2 times the Axion mass, and then hc, the strain, is g rho over m squared with some factors of pi and 2. Okay, so g rho over m squared is equivalent to the dimensionless strain. So you can just do that. You can take, so here's a nice summary from this paper by Hobbs et al. 2008, which was making forecasts for what the Parkes pulsar timing array would do, and it now has done, for constraining stochastic gravitational waves. So here's your frequency. Something like LIGO is detecting gravitational waves at a few hundred hertz. This is 10 squared, a few hundred hertz. The space-based observatory, like LISA, would detect gravitational waves at a few times 10 to the minus, about 10 to the minus 3 hertz. But the pulsar timing arrays sit less sensitivity to strain, but sit at much lower frequencies, about 10 to the minus 9 or so hertz. So here, in this plot, they showed the current limit, which I think at the time was from perhaps nanograv, and I'll show them shortly. And then the predicted limit from the Parkes pulsar timing array, and the predicted limit from SKA. And they showed that this would search for gravitational waves from cosmic strings, stochastic background there, stochastic background from binary black holes, and stochastic background possibly from inflation. And if you just take the shapes of these curves and translate them in the way that I talked about, you would get the current limits and projections that were shown in the Klemeninsky and Rubikov paper. You can read off the Axion masses that this is going to be sensitive to, 10 to the minus 9 to 10 to the minus 7 hertz here on the x-axis, translates into Axion masses between 10 to the minus 24 and 10 to the minus 22 eV. So this interesting range for fuzzy dark matter that we couldn't probe with the CMB, that we're kind of trying to probe with all these galaxy surveys. And the question is, what kind of constraint on the Axion density would you get in this regime? And this is what I'm going to show now. So here are the bounds updated in a paper that I actually only found yesterday looking for these figures by Porreiko et al. So for the Parkes pulsar timing array collaborations, this is a big paper with dozens of authors. And they show the constraints from the old nanograv results, which Porreiko and another collaborator of theirs wrote in 2016 or 17. So this was the nanograv analysis of 2014. There we go, Porreiko and their collaborator. In 2014, they had this bound on the dimensionless potential amplitudes. They use a psi and I use a phi. The bound on the amplitude from nanograv, from their newer nanograv analysis, and then in black and purple from the Parkes pulsar timing array. I'm pointing out here that they do a frequentist analysis and a Bayesian analysis, and the Bayesian analysis gives worse constraints than the frequentist analysis, and that's because it marginalizes over the unknown pulsar parameters rather than profile likelihood. So it takes into account better the uncertainty due to the modeling of the pulsars themselves. So the expected signal that you would get if fuzzy dark matter made up all the dark matter is the green line, and then they show the boson masses that is for up here. So if you took the frequentist analysis, they're just about able to rule out 10 to the minus 23 EV being all of the local dark matter. This is also something that we ruled out using, if you remember, reionization in the last lecture. But they're not getting down there with 10 to the minus 22 EV or any higher masses. But in this paper, they also reinvestigated the forecasts for what you could do with SKA for various different levels of exposure. So here it is. So here is, so in black is the previous limit from the Parkes pulsar timing array. And now they've translated it into the density of the local dark matter in the familiar GeV per centimeter cubed units. So the local dark matter is 0.3 to 0.4 GeV per centimeter cubed. This line is at 0.4. And then they've got, as a function of the boson mass up here. So the current PPTA limit is above the local dark matter density. Then they show the limit for SKA. So that the forecast for SKA, I don't know what the 10p, 100p mean, but and then they have like these 10-year exposure, various different SKA combinations. And you see that with these different SKA combinations, you can really come right below the local dark matter density for 10 to the minus 23 EV. And you come down below the local dark matter density by more than 2 orders of magnitude. So that means that this technique will give you constraints on the FDM fraction between 10 to the minus 22 and 10 to the minus 23 EV and below, corresponding to about 1% of the local dark matter. So that is the kind of quality of constraint that we were getting from the CMB. The CMB was giving us constraints on the local density at, the cosmic density at lower masses at about the 2% level. The improvements with CMBS4 will get below sub-percent, and they'll tank out at about this 10 to minus 23, 10 to minus 22 region. So pulsar timing really overlaps the CMB, the next generation CMB mass range, but also the next generation CMB precision. And they show also that you could start to constrain 10 to the minus 22 electron volts. Because the dark matter density at 8 kiloparsecs from the galactic center, that's what the current pulsars that they're using are. They're in the solar neighborhood. They're about 8 kiloparsecs from the Milky Way. But some of the pulsars that will be used by SKA are closer into the galactic center. So they've got so there's a higher density. So they've also shown here the density of dark matter at 2 kiloparsecs. So with an SKA, with one of these, you know, like their best SKA forecast, and using this pulsar at 2 kiloparsecs from galactic center, you would also start to be able to say something about 10 to the minus 22 EV at the kind of 10% level in the dark matter. So I think this is a really cool set of constraints, and really promising for the future as well. Okay, so that's the end of pulsar timing. The next third of today is another relativistic constraint, and it's a relativistic constraint again in this kind of approximately fuzzy dark matter regime. Yes?
Just a short comment. So you point out that the effective strain is proportional to density. So you can actually also use that by comparing pulsars at places with very different average density. Basically, I remember there was a paper where I did that. So comparing a pulsar timing of a very, like one of those 2 kiloparsec pulsars with the 8 kiloparsec pulsar, and then use the
Take a differential measurement.
Yeah, yeah. And I remember that potentially you can get orders of magnitude, 2 orders of magnitude, I think, better constraints by taking the spatial variance of the average density.
So rather than just the time variance of the signal, the spatial variance.
Because this, I think, all assumes an average density within the halo.
Yeah.
So you could use the granular structure, for example, so it makes a big difference if it's on top of the granule or in the trough between 2 granules. Yeah,
this was talked about a bit in the DiMartino paper. I think it was Ivan DiMartino and Tom Broadhurst. Yeah, yeah. So they used spatial. Yeah, so this paper by Ivan DiMartino, Tom Broadhurst, and some others. I think possibly Shive. They used the spatial correlation of the granules to extract the better signal. Yeah. There has been many variations on this theme looked at that I haven't covered. Another variation on this theme is that the local oscillations can disrupt, can affect type binary systems. Diego Blas and collaborators looked on variations on this if you also include the Axion couplings to matter. So if you say, okay, as well as locally affecting the pulsar from this gravitational effect, if you couple directly to the matter in it, you can also enhance this. Although you only get a large enhancement for scalar couplings, not for pseudo-scalar ones. But there are lots and lots of variations on this theme. But yeah, I forgot that you got a big enhancement with the correlations in the DiMartino paper. Yeah, so I think of that as a very interesting topic, and will be exceedingly interesting in the future. And it's quite nice because you don't necessarily need nonlinear. You need a level of nonlinear modeling in the sense that you need to model the Milky Way. So you need to say, okay, what's the Milky Way density profile in order to know this? But in a sense, that's something separate to the challenge of the FDM modeling. I mean, in an ideal world, you would make a self-consistent model of the Milky Way out of FDM, but it's separate from the from full cosmological evolution. It's more constrained realizations. So it's a different challenge in terms of modeling than what we've thought about for most of the rest of the lectures. Okay, so moving on to black hole superradiance. So yeah, this is another relativistic correction, and it's going to meet up with our discussion on fuzzy dark matter at the opposite end. So this is going to bracket fuzzy dark matter from the high mass end rather than the low mass end that we've come in from before. It's also going to make contact to the QCD axion, and it's going to bracket the QCD axion from the low mass end. So it's a really nice probe because it separates off fuzzy dark matter type models from QCD models and from opposite ends. And it's extremely powerful because of its generality, which I'll discuss. So, okay, we need to start with the Penrose process. So this refers to an enhancement of energy that you can gain from a particle if you send it near to a Kerr black hole. So the particle goes into the Kerr ergo region, and if the particle is moving faster than the rotational velocity of the metric field inside the ergo region, and then the particle splits into two, one of the parts falls into the black hole itself, into the event horizon, and the other one leaves. The one that leaves comes out with more energy than it went in with. And this is, I think, similar to scattering if you have a rotating cylinder, and you send the particle at the cylinder moving faster than the rotational velocity of the cylinder, it can come out accelerated from that process. And it's similar to other things like Cherenkov radiation. Okay, so when the particle then comes out with more energy than it went in with, it has to get its energy from somewhere, and it gets it by spinning down the black hole a little bit. So here's a cartoon of that process. Here is a projection of the horizons and ergo regions of a Kerr black hole in some coordinates, Boyle-Lindquist, I think. So here is the center of the black hole, the singularity, the dot. The brown region marks the edge of the ergo region, this special region that you need to enter to activate the Penrose process. And then the blue and turquoise regions mark the outer and inner event horizons of the Kerr black hole. So let's look at that now in polar coordinates in just the plane. So here is the ergo region again in black, and the outer and inner horizon in blue and turquoise. So this is the Penrose process. Particle goes in, 1, and splits into 2 plus 3. Particle 1 goes in, it has some positive energy, splits. The particle 2 then gets negative energy, falls in and becomes trapped inside the event horizon, falls into the singularity. But particle 3, you just do energy conservation, and this goes out with energy larger than E1, and it escapes to infinity. This is the cartoon of the Penrose process. This idea was built upon just in a kind of, I think, a kind of cartoon way, in the way we think of Dyson spheres, by Preston Tucholsky, who talked about using this process to make a so-called black hole bomb. Sounds like something out of a James Bond film or something. So Preston Tucholsky imagined surrounding the black hole with a mirror, and then having waves bouncing around inside here. So the waves have some overlap always with the ergo region and some overlap with the event horizon. So part of the wave goes into the event horizon, but part of the wave that's in the ergo region picks up a radiant, an enhancement via the Penrose process. But because this bounces around and around and around, this keeps on going on, and eventually the wave will extract a large quantity of the spin from the black hole. So in looking this up, I found a really, really nice video about black hole bombs and super radiance on this Kurtz, I'm messing up my German pronunciation, Kurtz's physics channel on YouTube. So I'm going to play you their cartoon about it, but I just need to start
Black
after the
holes are the largest collections of pure.
Okay.
How to steal energy from a monster. Take the supermassive black hole at the center of the Milky Way. We could steal as much energy from it as every single star in the Milky Way emits in a billion years combined. The easiest way to steal this energy is, oddly enough, to drop something into the black hole. We've seen that the regularity forces energy on us when we enter the ergosphere, which is a lot like being a whirlpool with space-time rushing round and around. If you're clever, you can use the water to your advantage and swim faster than before. In practice, this means sending a rocket into the ionosphere and making a trade with the black hole. We give it some mass energy, and it gives us some of its rotational energy. But it's not a fair trade. We get the better deal. Normally, if you fire a rocket, you exchange mechanical energy for kinetic energy. This is like pushing yourself forward in a swimming pool. But if you fire a rocket inside the ionosphere, it's like pushing yourself forward in a wave pool. The rotational energy of the waves gives you a much stronger boost than you could get just by pushing yourself. The boost from the rotation of the black hole is so big that you leave the ionosphere with much more energy than you exit. The black hole gives a tiny amount of its rotational energy to you and slows down a little. Obviously, this requires a lot of food. Fortunately, black holes aren't picky eaters. An advanced future civilization would probably harvest asteroids to drop them into the black hole when they needed an energy boost. But there's an even better way to get energy from a black hole, and oddly enough, it builds the biggest bomb any living thing can ever hope to build. The black hole bomb. We only need two things to build a black hole bomb: a fast-spinning black hole and a big mirror. The mirror has to completely envelop the black hole, which is similar to a Dyson sphere, a megastructure that harvests the energy of an entire star. Although our mirror would be easier to build, mirrors are simpler, and black holes are much, much more compact than stars. If we made the mirror 10 centimeters thick, the metal of a big asteroid would probably be enough material for a black hole with the mass of our sun. Once our mirror is in place, we only need to open a window and shoot electromagnetic waves at the black hole.
So this is now
You can
pressure
imagine what happens next by imagining tossing a ball to wall and it's coming back faster than a bullet. The waves hit the black hole at light speed. A small proportion of the waves falls past the event horizon to disappear forever. But a much larger amount sloshes through the ionosphere, where the black hole forces some of its rotational energy on them and amplifies them. They now begin super-radiant scattering, which are fancy science words meaning bouncing around between the mirror and black hole and getting stronger. Every time they go around, they are getting exponentially stronger. By opening some windows in the mirror, we can extract the energy from the waves as fast as they grow, which...
Okay, so that's the end of that lovely cartoon. I really like all of the, well, I really like everything about that cartoon. So yeah, brilliant. We'll actually see that the image they use to illustrate superradiance is actually from a real simulation that I'll show in a couple of slides. Okay, so let's get to axions and how does this happen in equations instead of cartoons. So we need to consider what the axion field does on the Kerr background metric. So all you need to do, you don't consider back reaction onto Kerr. You can show that in this case, the background doesn't change the metric, it only changes the parameters of the metric. It doesn't change its form, symmetry, so this is perfectly fine to do. So we just need to compute the box operator on the Kerr background. I say just, I haven't actually done this exercise myself because this is what the Kerr metric looks like in Boyer-Lindquist coordinates. So the S squared has some prefactor dt squared, looks a little bit like Schwarzschild, but because Kerr is rotating, you've got dt d phi mixed up with the rotation, and you've got dr squared, d theta squared, and then you've got this slightly different sine squared theta d phi squared, again because of the angular velocity of Kerr. So there's some Boyer-Lindquist coordinates here, I think, with Newton's constant set to 1. A is the spin parameter of the black hole. So if A goes to 0, you should recover Schwarzschild. And I'll be talking later in terms of the dimensionless spin, A star, which is just A divided by the gravitational radius, GM. So GM is the Schwarzschild radius. A divided by that is dimensionless and has is bounded to be between 0 and 1. So 1 is an extremal Kerr black hole, A star equals 1. And these two functions, sigma and delta, are just functions of the radial coordinate, the mass and the spin. And these are the things that you use to find the locations of the horizons. And you can see these functions written down, for example, in my paper with Matt Stott, or in any discussion of Kerr black holes, any textbook on GR. Okay, so we need to compute the box operator from that metric and solve the equation box phi minus d phi v equals 0. So just like we were doing for the Axion field and the Petre-Quinn symmetry breaking in the radiation dominated universe, we had box on FRW. Now we just need box on Kerr. We can try and make our lines a little bit simpler by using the symmetries of Kerr and decomposing the Axion field into the spheroidal harmonics S. So the spheroidal harmonics, they're like the spherical harmonics, but they're distorted because you've got the angular momentum. So they're not quite the same as the spherical harmonics, but it still looks kind of like a hydrogen atom, except these things are SLM, not YLM. And then you've got some radial eigenfunction R. Here I'm going to be slightly sloppy with notation in a way that I wasn't in papers on this, but here I didn't want to introduce much more. So just be careful that sometimes M will be the angular momentum quantum number and not the axion mass. And sometimes phi is angular coordinate phi, not axion field phi. Should be obvious from the context, but just if you're using these equations again, be careful. The thing that determines whether or not you have growth or decay of modes is obviously the energy eigenvalues. So if the energy eigenvalue is real, then you have just a stable mode. But if the eigenvalue has a complex part to it, then you can have growth or decay. So you can either have exponential enhancement or decay of a given mode labeled by Lm. So the omegas have Lm indices on them that I haven't written. You can simplify then the equation box into in some limits into an effective Schrodinger-like equation in terms of this new radial coordinate R star, which is the Wheeler, I forget the second person, the Wheeler someone tortoise coordinate. So d2 psi Lm by the R squared is simply equal to the energy eigenvalue omega, which you have to find, minus some effective potential acting on your eigenfunction psi Lm. So now here's the special bit about a massive bosonic field on Kerr and why it's a black hole bomb. You don't need to build the mirror because the potential, that effective potential for any massive boson on Kerr has a mirror caused by its own mass. So this is the effective potential. Here's the expression for it in terms of all the coordinates and functions that we had before, and the quantum numbers L and M with no subscript. So here Ma is the mass of the boson, and M with no subscript is the quantum number. So, but again, this isn't a quantum process, it's just a classical field, but it looks like the hydrogen atom, but it's for the condensate. Okay, so here's the black hole horizon at very small values of the tortoise coordinate. There's some angular momentum barrier, and then there is a rise in the potential again caused by the boson mass itself, which leads to the existence of bound orbits. And so these bound orbits are just like the orbits in a hydrogen atom, except now the fields are boson, so that they can have large occupation numbers, and then it just becomes an equation for the classical condensate. And the bound states correspond to things trapped in this region between the barrier and the mirror. So this now bound state acts like a mirror. So you trap your waves in here, but the waves, the solutions have some tail into the ergo region and into the horizon. So that's why they can now become involved in the Penrose process. So your waves are trapped, but they have the right tails to be involved in the Penrose process. So now the occupation numbers of some of these states can grow. So some states, Lm, will grow. What happens here then? So here's now an actual simulation of the superradiant process. So simulation done by Helvi Vitek, who's now at King's. She did her, I think this was during her PhD with Vito Cardoso. And you can solve the super radiant process. It turns out that it's tricky to solve for a massive scalar like the Axion, but it can be solved, and it was done in lots of gory detail in 2017 by Easton Pretorius. Vectors have a nicer timescales than scalars, but it applies to massive vectors, massive scalars, and massive spin 2 particles as well. But I'll only talk about scalars. But here's a simulation of the process with a vector, I believe. So you see, this is exactly the animation that was used in the cartoon, but now it's not a cartoon because it's got some axes on it, and it looks like what's this program that makes things look like this? I've forgotten the name of it. Visit. Right, this is there. There you make a visit. Okay, so here we go. Here's the waves growing over a few cycles. Brilliant. Okay, so this is a thing that doesn't just exist in cartoons, but exists in equations. So how does this work to get you now super radiance from an axion field? So you have an effective gravitational atom. So it looks like the hydrogen atom, but with the spheroidal harmonics. And it has an effective coupling constant alpha. The effective coupling constant of this atom is G times MA times M black hole. You see that this is dimensionless. Mass squared, G has units inverse mass squared. It's dimensionless coupling constant. And it's related to the ratio between the Compton wavelength of the axion and the gravitational radius, the Schwarzschild radius of the black hole. If you have imaginary eigenvalues omega, you get a growth of occupation number of that orbital. And the time dependence of the black hole mass, which is also the time dependence of the spin and the energy, and you can see this system in my paper with my stat, is proportional to the super radiance rate gamma SR, which itself is proportional to alpha to some power times the axion mass. Turns out that when you do a whole bunch of tricky solutions to these to the relevant equations, when alpha is of order 1, it maximizes the super radiance. And in order to have this growth of modes, of course, the super radiance timescale should be the fastest timescale in the problem. So we're neglecting other astrophysical things that are happening, for example, accretion. So in order for this to work, it better be the fastest timescale in the problem, so it beats anything else. And so you see that alpha is equal to 1, super radiance is maximized approximately when the axion Compton wavelength is of order the size of the black hole horizon. So now you can use a little bit of intuition to say what axion masses will affect what black holes, just by dimensional analysis kind of now. Okay, but the Penrose process itself requires that the angular velocity of the horizon is larger than the phase velocity of the waves propagating inside it. So the phase velocity of the waves is given by the magnetic quantum number m, and omega now is our energy eigenvalue. So we only have our exponential growth when the following condition is satisfied: a star the dimensionless spin, m the black hole mass, and small m the magnetic quantum number. So you have this exponential growth, and you populate your modes, but it shuts off when the modes become so populated that this condition is violated. So super radiance only goes on for a certain amount of time, so it means that super radiance saturates after extracting some finite amount of mass and spin from the black hole. So then you can write down what the final black hole mass and final spin should be, given that you began in some initial state. So when the radius of the black hole is of order the axion Compton wavelength, we don't expect to see black holes with a large amount of spin. So you extract some amount of spin, but it should get a star below 1. So basically, just from this condition and saying it has to saturate somewhere, we can say, okay, we shouldn't see certain extremal black holes with large values of spin. It turns out you can work all this out in lots more detail, but I'll leave that to the references, but I'll show you what happens. So we can use this to constrain the existence of axions or any massive boson. We can use it to constrain a possible massive vector field, the mass of the photon. You can get constraints on the mass of the graviton from this. And order of magnitude, they look like the Axion constraints. There are order 1 factors that come in from different spins. Okay, so it's a very, very generic process because you've got exponential amplification of fluctuations. You can start this process from a vacuum fluctuation. So you don't need to have dark matter axions around. You just have some vacuum fluctuation, and then very quickly that will get populated into the classical regime, and now you can just think about ordinary superradiance. So you don't need a background density. So the constraints apply independently of the axion density. So you can just rule out all values of the cosmic density at a given mass. You also don't require any non-gravitational coupling to start this problem. Non-gravitational couplings, as I'll show in a few slides, can shut it off, but you don't need any to start it. So it's a completely generic solution. So black holes of certain masses and spins should not be observed if axions of certain masses exist, as long as the superradiance timescale is shorter than the timescale. Any timescale involved in the black hole, accretion, the saltpeter time, the Eddington time, things like that. So measurements of black hole masses and spins exclude certain axions. So we know that black holes of certain masses and spins exist. You can measure the spins, for example, from the red shifting and blue shifting of certain emission lines in the accretion disk around the black hole from X-ray measurements. I think you can do it from like iron lines coming from the accretion disk that you observe in the X-ray. Okay, so here's a really nice GIF that Matt Stott made that shows you how you get constraints from this. So here he's got the region that should be excluded for a given axion mass, and in the plane of the black hole dimension, the spin and the black hole mass. And he moved, and then he's got the data of observed black holes, just a few to make it simple to see, modeled as 2D Gaussians with no covariance between the mass and the spin sitting in this plane. He moves the region across these measurements and shows you what axion mass that corresponds to by coloring the region according to the axion mass in the color bar here. So these, and of course, if this region that should be excluded overlaps with these data points, you get an exclusion on that axion mass at some probability that you can calculate just from the overlap of the region with the 2D Gaussian. So here we've got black hole masses of kind of about 10 solar masses, these things that you can get from ordinary stellar evolution. And they're excluding axion masses in the kind of 10 to the minus 10 to 10 to the minus 14 eV range. On the right-hand side, running at the same time, Matt shows you the exclusion probability that you get from computing this overlap integral as a function of the axion mass. So you see it rise when they start to overlap, and he shows what it does for the different black holes and the total, and it continues to be excluded for a range of masses until now your region drops away from your measured black holes and the exclusion probability drops to 0. So this is the statistics that we're using here, and that we're going to use to work out the what axion masses are excluded. So Matt and I did this, and we did it for a big compilation of black hole mass and spin data. So we took all of the normal stellar black holes that we could find in the literature, plus all of the supermassive black holes that we could find in the literature. We treated them all on an equal footing. So we just combined the likelihoods and modeled them as 2D Gaussians and computed the exclusion probability. And this is what it looks like. So Matt's very nicely kind of put it all together on one plot for you, so you can see it all at once. So if you look at the bottom x-axis and the left y-axis, you see all of the black hole data labeled by mass and spin. The blue and orange data points. The blue data points are stellar black holes, the orange data points are supermassive black holes. Then the region that's excluded in that plane for a given axion mass are the colored regions, and the axion mass that you see is excluded is labeled by the color bar there. So you see that like the 10 to the minus 12, 10 to the minus 10, 10 to the minus 11 masses overlap the data, so they're excluded. Then if you look at the topmost x-axis and the rightmost y-axis, map plots as a function of the axion mass, the exclusion probability. So you see it all at once. And so you see that axion masses between about a few times 10 to the minus 10 and 10 to the minus 13 EV are excluded by the stellar black holes, and axions between about 10 to the minus 16 and 10 to the minus 20, 10 to the minus 19, 20 EV are excluded by the supermassive black holes. So we've really made contact now with the bounds on fuzzy dark matter coming from Eridanus 2 and from large scale structure. They kick in, large scale structure definitely kicks in at 10 to the minus 23, 10 to the minus 21. We showed Eridanus 2 kicks in about 10 to the minus 20, 10 to the minus 19. We've really got lots of overlap with our constraints now. There's a slight complication to this story.
Sorry?
Yeah.
One question, how good is the assumption that the spin and the mass, I mean, and the errors are not correlated, or how important is it for the constraints?
I don't know. I don't know at all. So we did a very simplistic treatment of the errors. We just, a lot of the time we weren't given, we didn't go and look for the likelihoods from the experiments. We just looked at what was written down. If they said it's 68, we assumed that's 1 sigma, and we assumed no covariance. I have no idea how important that would be. I believe we looked a little bit at covariance, but yeah, I don't know. I think it would be, and we also, well, to compute the overlap integrals, we made this approximation where we could collapse the x and y errors into just one effective y error as well, which is also an approximation, and I think only holds at the level where you don't have covariance. So it would probably be worth doing this in a more statistically rigorous way.
I guess it depends on how many black holes you have observed in the kind of relevant mass range, right? Because if it's many of them, it's probably the covariance is not too important, and I guess it's fine to just ignore it. But yeah, I mean, where the limits are not too strong, it might play a role. But okay, cool.
Yeah. So I think for the stellar black holes, these are, I think, relatively well understood measurements, and you see that there are lots of them. So you're probably not going to change this nice 10 to the minus 11, 10 to the minus 13 explosion. Supermassive black holes, it's going to make a much bigger difference. There's a smaller density of points, and there are these leftmost 2 supermassive black holes have quite large errors on the spin, and of course this affects very much the shape of the exclusion at intermediate axion masses 10 to the minus 15, 16 EV. So for the supermassive black holes, it would be very important. Yeah.
Okay.
And these, as I understand, are much less well understood measurements. Yeah.
Okay. Yeah. Cool. Thanks.
Sorry, one question from my side.
Yeah.
So if I understand the plot correct, so there's this window which is not really covered, right? You have these 2 excluded regions, and is there one possibility to close this, or? So
I would call this somewhat the one of the axions from hell. The other axion from hell is the kind of 10 to the minus 3, 10 to the minus 3, 10 to the minus 2 EV PCD axion. This is another axion from hell. It's not constrained by black holes simply because we don't know about intermediate mass black holes. Maybe this is why, right? Maybe there's some reason that they don't get any spin and they get disrupted by these axions. It is, from direct detection, about in the range that you can access with CASFET. So 10 to the minus 15 EV is about 1 hertz. But then of course you need the couplings. I haven't thought about anything astrophysical that you can use to constrain this axion. It does lie in the frequency range for pulsar DeSigo, these intermediate range gravitational wave observatory. So maybe there's something you could get from DeSigo about constraining this axion. Maybe you could do it from a pulsar timing type thing, but maybe you would also do it if there were intermediate mass black holes. This is also something you could probe with DeSigo. An interesting thing about this mass is 10 to the minus 15 eV is the axion that you would get from the model-independent axion in string theory or M theory related to the gut scale coupling. And this came up in this M theory constraints on the Axiverse paper by Bobby Acharya and company. This mass scale is picked out. And yeah, so I think if you had the model-independent axion, heterotic string, you know, one gauge coupling from your second D8, this is the axion you'd get out. And it's not excluded by any current measurement. So it's an interesting mass scale. It's been predicted in a number of different papers from string theory, and it's not excluded.
Okay, thank you.
It's a good mass scale to target. So if you have any ideas how to rule this out, it's a very good one to target because nothing else covers it, apart from maybe Casper and direct detection. Bodo, you had a question?
Yeah, so in your constraints, you don't include the possibility that these spinning black holes are on the regulation trajectories, right?
What do you mean?
So, I mean, they spin down the black hole, they will be stuck at some point at these regular trajectories where the energy is basically transferred between different shells of your gravitational energy.
Right, yeah, so we didn't include the transition effect. So you would observe gravitational waves or other emission if the black holes are stuck on the edge of these excursions. That is discussed in detail in the papers by Alvanataki and company.
But this is not.
It is not included here. We just say only exclusion. We're only looking for exclusion, not for evidence for, which you would get. So those observations could be used as evidence for a certain axion. We're only using exclusion.
I don't know what time scales how long they will be generally stuck there. So probable it is that these black holes are just the ones that are stuck there.
I think from like stellar black holes and the processes you're talking about, there are prospects for finding evidence from the QCD axion from these processes using like LIGO searches for stochastic gravitational waves. So there's a small window of masses for the QCD axion just below what's excluded here, about 10 to the minus 10 eV, where those kind of processes are important for stochastic gravitational waves in LIGO.
Yeah, I'm not sure if this is what this question what this leads to, but wouldn't these black hole spirals be also a source for Axion productions? Because it just needs vacuum fluctuations to kind of produce them. Yeah.
So the axions in the cloud don't get away. So they're the cold ones. But you can have, and this is related to Bodo's question, emission of hot axions from the cloud, a process I'll show on the next slide. So you can have, if the axions have self-interactions, like 2-to-2 production where one escapes the cloud, and this will produce relativistic axions from the cloud, and you could observe those. So and again, I think this is discussed in some of the papers by Alvanataki and company. So you produce some axion in the cloud, but around the black hole, you've got like a bunch of stuff, including magnetic fields. And then that axion, if it couples to photons, can convert into visible photons. And so you would have a source of relativistic axions turns into photons, which you can then observe. This would be in like the sub-radio band. So yeah, definitely a source of relativistic axions. I don't know about it as a source for dark matter axions, but you could have, like, for example, the black hole at the center of the galaxy creating a cloud of axions that affects the density profile in the galaxy. This has been looked at, but I can't remember by who. Okay, So the next two things to say about black hole superradiance is I have simplified this story in a number of ways. One of them is I've only included the Axion mass term in the Klein-Gordon equation. So the Axion interactions can shut down this process. So let's take our classic cosine Axion potential. Let's expand it to power 4 in the Axion field. So I should have plus higher order terms on the right-hand side. So I get a mass term and I get a lambda 5 to 4 coupling. So you can then compute lambda in terms of the Axion mass and the K constant and ask when the 2 to 2 interactions can shut down the superradiance. So if the rate of production of axions from these 2 to 2 interactions, which are attractive, is larger than the superradiance rate, they can cause the cloud to collapse. And this is known as the boson-over process. So you can work out these rates and the boson-over rates and just work out when they cut off. Because the coupling constant lambda is inversely proportional to the decay constant, so that 4 powers of decay constant from cosine, so lambda goes like m squared over f squared. At higher values of the decay constant, the self-interactions become less important. So if I take the decay constant up, at some point the self-interactions become so strong that they shut off superradiance. That's what this looks like. This is just for now a single one of the stellar black holes, LMCX1, so probably in the Large Magellanic Cloud. The exclusion region of the Axion mass is the same as our exclusion before, about 10 to the minus 13 to 10 to the minus 11 eV. As the decay constant goes to infinity, 1 over the decay constant goes to 0. As I lower the decay constant, increase 1 over the decay constant, at some point the boson-over takes over and the exclusion goes away. So here Matt's plotted the 1, 2, and 3 sigma exclusions for different values of the decay constant. Now you can really say, does this exclude the QCD axion? Because for the QCD axion, we know the relationship between M and F. We put it on as a line, and the answer is yes, this does exclude the QCD axion. So it excludes the QCD axion with decay constants between about decay constants somewhere near the Planck scale, and masses about 10 to the minus 11, 10 to the minus 13 eV. So this is a constraint on the QCD axion. You can also do the same game for the supermassive black holes. Matt hasn't done it, so I'm lifting the plot from, I'm going to lift the plot from Arvanitaki. The takeaway statement here is though that the stellar black hole superradius constraints apply roughly for axion decay constants larger than 10 to the 14 GeV for an axion-like particle. They don't apply to low values of the decay constant, significant for the large volume scenario in string theory, where the decay constants are 10 to the minus 12, but it does apply for gut scale decay constants. Let's do it for supermassive black holes. This is now from the Arvanitaki paper. So here is the exclusion from supermassive black holes. The range we saw before, they used fewer black holes, so it doesn't join up as nicely. Goes from 10 to the minus 18 to 10 to the minus 16 EV. The supermassive black hole constraints shut off due to boson-over at about F of 10 to the 16 GeV. And this also gives you constraints on the QCD axion, but only at like very super Planckian decay constants. And the last thing to say about black hole superradiance before we move on to mini clusters in the last 15 minutes is that you can use this to constrain the number of axions. And this is something that Matt and I did last year. So, okay, this is the only bit where we're going to come across our string theory axion mass distributions. So the mass distributions in string theory have log space support. That's because they came from this exponential, the axion mass depends exponentially on the moduli for reasons that we saw. And so they have log space support in general. So let's just imagine that they have a log normal distribution. So in some limit, this goes to log flat, whereas in the limit that sigma becomes large, this looks log flat. In the limit that sigma becomes small, this becomes almost linear support. So let's consider a log normal distribution parameterized by 2 parameters, mu bar, the central mass, and sigma, the log space variance. And just populate this distribution with large numbers of axions. this distribution, it can sit quite far away from the black hole superradiance constraints. But once you put in a large number of axions, you'll start to have a non-zero probability of one of them appearing in the tails in the superradiance band. So for this distribution, a large number of axions starts to become excluded. And we computed that just with some simple probability with overlap using the usual AND rule for probability. So you write down the probability that your model with parameters theta and number of axions on X is allowed is the probability that a single axion is allowed times the probability distribution function of m given the parameters theta. So here the parameters theta are mu bar and sigma. And you just take the product of this with the number of fields that you have. You can compute the exclusion on nx and theta. So this is what we did. Here's the exclusions. The curves tell you what the central value of the axion mass is. Sigma labels the width of the distribution, and n is the number of axions. So you see large numbers of axions are excluded, small numbers are allowed, and depending on how wide you make your distribution, this goes away because you have a very wide distribution. The region excluded by black hole superradiance only covers about about 3 or 4 orders of magnitude. So once your distribution becomes too wide, again, the probability of landing in those windows drops again. And we get these exclusions. And it's quite neat that if you set your central axion mass, let's say it's 10 to the minus 15 eV, chosen by the gut scale, that's one of these curves here, then quite a large range of log space support for your distribution. Sigma is between 100 and 0.1. Large numbers of axions are excluded, where large numbers, I draw on here the value 30, which if you recall is the peak of the Kreuzer-Skarka distribution of axion numbers from reflexive polytope constructions of Calabi-Yau manifolds. Okay, so black hole superradiance is great. You can use it to constrain axions and any massive scalars, any massive bosons really generically. We can now combine all the constraints that we've seen, all the gravitational constraints we've seen on fuzzy dark matter and related models onto one plot. Let's do that. This is a plot that was in the astrodecadal survey that isn't on the archive yet, but will be soon. Here we go. Constraints on the cosmic axion density as a function of the axion mass, covering 22 orders of magnitude. We can do this. And here's all the constraints we've seen. So the shaded regions are currently excluded. The open regions are projections. So here's the shaded constraint from the CMB. Strong constraints on the axion density at the 1% level, covering a number of orders of magnitude. Here's our reionization constraints up here, Lyman alpha constraints, pulsar timing array, improvements on Lyman alpha, improvements on pulsar timing, improvements on the CMB. Here's Eridanus 2 constraints that we heard about from Jens. Here's black hole superradiance. It doesn't care about the axion density. Eridanus 2 gets really strong constraints on the density because of these resonance effects. And here's the region predicted from our formulae for the relic density in lectures 3 and 4 by gut scale decay constants. So all of these probes are probing axions with gut scale decay constants that are subdominant in the dark matter over many, many, many orders of magnitude in the mass. I'll just highlight the gut region because it's not very visible on this plot. The part of the gut prediction that we're not quite covering is we need improvements in precision in things like the pulsar timing, Lyman alpha, CMB. If I increase the decay constants to values larger than the gut scale, that's excluded. So we've made exclusions on decay constants larger than the gut scale already, and we are starting to make headway into the gut scale region of light axions. But then, as Jan pointed out on the other end, there is this axion from hell around 10 to the minus 15 EV that I don't know about any constraints on. So, yeah, lots and lots and lots of constraints. For those of you at Göttingen, I'm going to go over this again in a more cartoon fashion in my colloquium in a couple of months' time. Okay, So that's it for cosmological and gravitational constraints on light, fuzzy dark matter type models. In the last 15 minutes, I'm going to go over quickly another gravitational probe. I'm going to go over constraints from the QCD axion in scenario A due to microlensing. So remember, scenario A and B was the Petrie-Quinn symmetry broken before, or was the Petrie-Quinn symmetry broken after or during inflation for A and B? All these ultralight guys with large decay constants cut scale require you to be in scenario B, where the symmetry is broken during inflation. But the QCD axion can be in either case. So let's think about, are there any purely gravitational astrophysical probes of the QCD axion in that scenario A? And that's what this mini clusters and microlensing section will be about. So recall the classic axion window. So the QCD, this should say A. QCD axion scenario A has in principle no free parameters once you fix the relic density. There are these uncertainties that we talked about on the relic density due to string decay, but you can still bracket the axion mass, say somewhere between 50 and 200 micro eV. Here's the picture of that formation mechanism from having done those slides. So here we have the axion field theta between minus pi and pi, and it has order 1 fluctuations. Theta takes on all different values between minus pi and pi, variation on scales of order the Hubble parameter. What does this do cosmologically? That's what mini clusters is about. So again, this should be scenario A. Axions in scenario A depart from standard cold dark matter in their initial conditions. So the post-inflation symmetry breaking gives us large field fluctuations that we saw and axion dark matter relics. This extra source of fluctuations produces new forms of structure formation. So here is the power spectrum that we're now very familiar with. Turns over at matter radiation equality, goes down. Galaxies and nonlinear physics happens around wave numbers of 1 to 10 inverse megaparsecs. But if we continue that all the way to 10 to the 9 inverse megaparsecs, then you see what the mini cluster symmetry breaking fluctuations do to the power spectrum. They give you a new source of white noise isocurvature power at low amplitude, but eventually it takes over the ordinary power spectrum at wave numbers of around 10 to the 5 or 6, this is for the QCD axion, and leads to this formation of mini clusters due to this enhancement in the power. So what are mini clusters? They were first talked about in 1988 by Hogan and Rees, and it came from saying what happens to these large amplitude perturbations. So you can say that they'll form an object of some mass, where this mass is given by the average dark matter density in the horizon, or in the patch of size L. So we have some order 1 density fluctuation on scales of order L, and this gives us some mass that we can compute. And the expectation is that these large perturbations collapse into bound objects of this characteristic mass. So let's try and move on with this idea. What is the mass? What are the objects? What do they do observationally? So first of all, we need initial conditions. We talked about this already in lecture 4. You have to solve the Petrie-Quinn symmetry breaking problem in the Axion system on a lattice, which means using a finite difference method or a spectral method. And here are the initial conditions taken that many people here are working with already, taken from the paper by Vaccaro et al. So okay, this is just showing in more detail what the axion density is from the cartoon we saw before. So you see there's these large density contrasts of up to 10 squared on scales of order 1 in their chosen units. So what do we do with these? These things need to collapse. So we have these large overdensities. They collapse at early times. They lead to small, tightly bound objects. And if we assume that those objects remain bound and survive until the present and form structure just as point particles at later times, we have macho-like objects inside galaxies. Macho meaning massive compact halo object. So we have these small, tightly bound objects inside galaxies. Or do we? And what is their spectrum? So we need to know a lot of things about them to try and constrain them. We would like to know their mass function. We would like to know the density profile. We would like to know the fraction of dark matter that actually ends up in these objects. And we would like to know the survival probability of these objects to the present day. So what is the final FMC? FMC here is the fraction in mini clusters. What is the initial amount of these objects? But then what happens as they form structure later? So, you know, they're going to form structure like the Milky Way, they're going to fall in to dark matter halos, maybe they get tidally disrupted by the stars, who knows? How do we solve this problem? 1, 2, and 3 can be solved either using semi-analytic models, the type we've also heard about for fuzzy dark matter, or by simulation. So you can do, and just for the same reasons that we talked about with fuzzy dark matter, this is just fuzzy dark matter, but on a smaller scale, corresponding to the QCD axion mass. We can use sometimes n-body simulations in the same situations like we can for fuzzy dark matter that Jens talked about, or we can do full FDM-like simulations inside this and try and look for the equivalent effects, like axion stars and cores inside mini clusters, say what happens to the wave-like effects. And 1, 2, and 3 are both amenable to these different approaches. Number 4, the survival probability can only really be solved using semi-analytic models, and that's because you've got no chance of starting with fluctuations, as we'll see, at 10 to the minus 11 solar masses and evolving them all the way to the present day and forming the Milky Way. You've got, or from the power spectrum, you've got no chance of starting with fluctuations at 10 to the 9 inverse megaparsecs and following them all the way to a megaparsec. This is just too much dynamic range. You're never going to make the Milky Way out of these things in one simulation. So you have to use modeling to get the survival probability. And all of these questions have been addressed in the literature, and I'll only talk about things really in the literature. So we need to estimate the mass. Recall that we have we want to estimate L. So this is the axion equation of motion before gravity kicks in. The axion begins oscillating at this temperature T os. So we can infer that the length scale in the problem from the wave number is of order 1 over h. I want to now fix my various parameters. So in this scenario, the scenario A, the axion mass and decay constants are no longer independent once you fix the relative density. That's because you've just got this fixed average contribution and string contribution to the relative density. So here are the contours of fixed relative density for different out models, temperature dependence of the mass, axion mass, decay constant, QCD axions align, there it is. You can convert this into masses using the formula that I gave you before. Just find what T OSC is using G star and things like we already discussed for the relative density in lectures 3 and 4. And you can work out the mass of these objects that you expect. For the QCD axion, you expect these objects to be something like 10 to the minus 10, 10 to the minus 12 solar masses, depending on various uncertainties in the calculation. I think I might have found a factor of 20 in my own previous estimates before, but I already discussed that with people who are interested. Okay, next thing we need to know is we need to know the density profile, the radius. We can try and, this was estimated, so I should have the reference here, Colburn to Katche. You can do spherical collapse in the radiation dominated era. So just like spherical collapse in the matter dominated era tells you that the virial overdensity is about 200. You do it in the radiation dominated era. These things are large overdensities, they collapse at early times. You find the virial density, should be an approximate symbol here, is a fit, is 140 times the density at the time of collapse, rho bar times 1% collapse cubed, times this funny factor that depends on the overdensity of the perturbation itself. This factor delta cubed 1 plus delta. So collapse occurs at some redshift ZC, which can be earlier than matter radiation equality. Normal fluctuations only begin collapsing once matter domination kicks in. So here, the virial overdensity actually depends on the overdensity itself. That is because large overdensities give earlier matter radiation equality in that patch where you have your overdensity. And thus the mini cluster radius is fixed by the mass and the virial overdensity in the following way. You just write what the mass is in terms of the virial overdensity and the virial radius. And the virial radius you can now compute from this in terms of the density of the mass. Here it is, 10 to the minus 6 parsecs for some reference parameters. You have to solve the axion field dynamics, like was done in the Vaccaro paper. And when you do this, you find the distribution of different overdensities for your initial seeds. So this would predict that you get a distribution of different sizes of mini cluster for fixed mass, but you've really got a 2D distribution, different masses, different sizes of mini clusters. How can we start to quantify this? What is the distribution of this delta parameter? So now I'm going to go right back to some really early simulations. I called them to Katchev in 1996, because I think they show it in the nicest way. What is the distribution here? They use phi instead of delta. What is the distribution of overdensities? So this is the cumulative distribution. With a wide non-Gaussian distribution of overdensities. So this ether labels the time of their simulation. 4 is the final time. So they're kind of trying to show that you've converged to some distribution. With a wide non-Gaussian distribution of overdensities that continues or possibly continues to very large values of overdensity. And you can fit this with some distribution. We also need to know the density profile. If you do what's called self-similar infall of an isolated patch, you can predict the density profile and it has some power law form. The question is, what is the radius and characteristic density of this profile? What is this rho 0, r0? Are they the virial radius and virial overdensity? I don't know. I'd like to answer that question. This also gets modified by secondary infall. Some scale radius should appear. Maybe something more like NFW. These are all open questions, I think. Axion stars should also form. How is this related to all the process that we've heard about, condensation, core halo mass relations? I don't know. But what we can say is something about this initial power law. The top hat initial mass profile predicts some slope parameter, and it will predict 9/4. Is this correct? This has been investigated by a number of different people here at Göttingen, and I'm not going to go into the results, but for example, some n-body simulations were done by previous master's students, and these have been shown at conferences like a number of years over a number of years by Jens, Felix's simulations and Ruslan's simulations. So here is the n-body collapse from the kind of initial conditions we saw before into gravitationally bound objects. And these simulations find some mass function and some power law and a density profile a little bit steeper than that 9/4. And this is something we need to understand. I've only got a couple of minutes, so I'm going to try and get through stuff. Tidal stripping, you can look at this. It was looked at in a paper by Dr. Chayev et al. And it turns out that the survival probability, so the fraction of mini clusters that survive, is larger for larger overdensities. So your more dense, your more compact objects survive tidal stripping more. And significantly for the constraint I'll show in the last slide, the very densest objects with largest values of this overdensity parameter phi have only a very small fraction of those mini clusters will be destroyed. So the dense objects, the ones that are going to be important for lensing, should actually survive all tidal processes. So the ones you don't care about get stripped away, but the ones that you care about survive. So that's important. So gravitational microlensing, it's a thing. You can compute the magnification of microlensing. It defines something called the Einstein radius, which defines a geometric tube. So objects are flying about, you're looking at a source star, object passes between you and the source star at some impact parameter from the line of sight, it amplifies the light from the source star. If the object comes within a certain tube along your line of sight, it will create a large magnification. So you can define a geometric tube between you and the source through which the lens has to pass to create a lensing event. This is called the microlensing tube, and it has the shape corresponding to the Einstein radius. So then, given your host halo model, given your model of how these lenses are moving around in the halo, just according to the standard halo model, NFW distribution, Maxwell velocity, you can compute the probability for lenses to cross this tube. So then you can compute the rate of events that you should see. This is used a lot to compute constraints on primordial black holes. Here it is from the paper by Nikora et al. I want to point out these two constraints that are really nice and cover many orders of magnitude are for microlensing, HSC, Subaru hyper-supercam, EROS. Mini clusters sit right here in a range that is possibly covered by HSC, but maybe in this gap here. Where does the gap come from? The gap comes from something that has been addressed for primordial black holes, but not for mini clusters. It comes from so-called finite source size and wave optics effects that decrease the microlensing development. So can we constrain mini clusters with microlensing? The answer will be definitely if we don't include this finite source size effects. Once we include finite source size effect, this all becomes very dependent on what is the mini cluster mass, thus what is the QCD axion mass, where does the relative density come from, and what is the mass function of these objects. So because of this opening of the gap, these constraints very much depend on all of these modeling effects. So in the interest of time, I'm just going to stop here and say lensing can give you constraints on the QCD axion. Actually, I'm going to slip to my final slide. I'll show you the final slide. Okay. No observed lensing events. QCD axion can constrain the mini cluster fraction. So we can constrain the mini cluster fraction in the QCD axion band using gravitational microlensing. However, we don't know the prediction for this value of the mini cluster fraction, the density profile, and the mini cluster seed mass well enough to really be sure of this. Have we already ruled out the QCD axion in scenario A? How will observations improve in the future? These constraints do not include finite source size effects. I don't know what's going to happen with this, but I think that you can use microlensing to possibly exclude the QCD axion in the classic window. But lots of uncertainties, lots of modeling needs doing, but I think it's exciting. That is the end of our gravitational probes of axions. So yes, questions?
No, can you just remind what is the small n equals 0 and
Okay. The small n here, I'm doing axions and axion-like particles. N labels the temperature evolution of the axion mass. So 3.34 is the model for the temperature evolution of the QCD axion and the interacting incident on liquid model. N equals 0 would be some axion-like particle with constant mass. So that's why the 3.34 is the one you should follow for the QCD axion. Yeah.
What do you mean by finite size in this context?
So what I mean by finite size is this lensing tube that you need. So okay, so here's what we're looking at. Let's say we're just looking at a point star, it's a star, and then there's some tube around that star which an object needs to pass into to amplify the light of the star. Then it just amplifies the light of the star by some amount because the star is a point. But for these very low mass objects, this ring itself is very, very small. And it can actually be smaller than the size of the star. And when it is, only the light of the star within the ring is amplified significantly. So you only magnify a fraction of the light of the star when the lensing tube gets very small. So you have to include that the stars aren't just 1 pixel. And that's why you use some amplification. And that's why the constraints go away for very low masses, because you just make the size of the tube smaller and smaller and smaller until eventually it goes away and you enter these femtolensing regimes and things. So, yeah. Problem was that effect was not included in these constraints. And if the QCD axion mini clusters are too light and their mass function doesn't extend enough, then they'll be sitting in this finite source regime and you'll have no lensing constraints. From traditional microlensing, there are other types of microlensing that can maybe get around this. But for this type of normal survey of HSC looks at a bunch of stars in M31 and just waits for them to be lensed, you could try and look at lensing of other objects. Okay, if there are no more questions, I'll stop there and say that tomorrow and Friday, we will move away from astrophysics completely and look at direct searches for axions on Earth from their direct interactions. And we'll focus on the QCD axion, but we'll talk about some other axions as well. Right, cheers.